standing waves. Up till now we have discussed the superposition of waves and the interference of waves along a stretched string. So if two waves of the same wavelength and same amplitude, same frequency traveling in opposite directions along a stretched string, what will be the resultant wave? So let us discuss the situation. Consider two waves along a stretched string as shown in figure A and B. One wave in figure A is moving to the left and the other is moving to the right. Both the waves have the same frequency, same wavelength and same characteristics, but they are moving in opposite direction along a single string. Here they are shown separately, but they are moving along a single stretched string. So what will be the resultant pattern? In this situation, when this is the situation, wave A is moving to the right, wave B is moving to the left along the string. So at this position in time, if you look, the crest is on the crest, that is, the crest and troughs of these will meet at this time. Let we call this time t is equal to 0. So if we apply the principle of superposition, that is, if we add the individual displacement algebraically, so it gives rise to a higher displacement. That is, the displacement of the net wave or the resultant wave is double as the displacement of or the amplitude of either wave. So this is the case of constructive interference. Now this wave is moving to right and this is moving to the left. So as time passes, the crest will not be at the position of the crest of one another, and similarly the valleys will also travel to different locations. So we look at the situation after time t is equal to t by 4, where capital T is the time period of the wave. At 1/4 of the time period, if we look, this wave will travel some distance to the right and this to the left. It should cover a distance 1/4 of the lambda in t by 4 seconds. So this wave, the 0 of this wave is shifted to this position, and of this one is shifted forward, so its peak arrives over here. So here we see in this situation that, look at this position, the peak of this wave arrives at this location while the value of this wave arrives, or the crest of this wave arrives and the trough of this wave arrives at this position. So at this position, these two waves will completely cancel the effect of each other, and the resultant wave will have a 0 amplitude or 0 wave displacement at this position, denoted by this dot. This dot means that at this position the displacement of the resultant wave is 0. Now, if we look at the situation after another 1/4 of the time, that is after t is equal to t by 2, so what happens that again the crest of this wave and the crest of this wave arrives at the same position, while their troughs also arrives at the same position. So again giving rise to a double displacement, that is the displacement or the amplitude of the resultant wave is doubled at these locations, at this location and at this location. But again you see that at the point, this point, again the displacement is 0. This is the resultant wave. This green one is the resultant wave. Figure A is a wave that is traveling to the left, figure B is a wave traveling to the right, while figure C shows their resultant. So if we go further in time, that is if time passes and after t is equal to 3t by 4, if we look at the situation, again the valleys of this wave and the crest of this are at the same positions. So again cancelling the effect of each other, and you see that the net result is 0. That is the displacement of the resultant wave is 0. That is a totally destructive interference. Where here you have a fully constructive interference, at this time you have a fully destructive interference, here again fully constructive interference, fully destructive interference, and after time t is equal to 1 time period, again you have a fully constructive interference. But there are some points which are denoted by the black dots have 0 displacement always. These points are said to be the nodes, while the points that can have maximum displacement, these central points, they are known as nodes. So this is the graphical or the conceptual description of a standing wave. If two waves of the same wavelength, same amplitude and same frequency travel in opposite direction along the same stretch string, their interference with each other produces a standing wave. So now let us discuss the mathematical description of the standing waves. To analyze these waves, we write their equations as the wave that is traveling to the right in the figure is described or is represented by ym sin of kx minus omega t. The wave that is moving to the left is ym sin of kx plus omega t. That is, this wave is ym sin of kx plus omega t, and this one is sin of kx minus omega t. Now these two waves are passing through the same stretch string. So apparently we will apply the principle of superpositions of the waves to find out the resultant wave or the wave function of the resultant wave. So the wave function of the resultant wave y prime of xt will be equal to the sum of the displacement of these individual waves, that is equal to y1 of xt plus y2 of xt. Putting the values of y1 and y2 in this equation, we get ym sin of kx minus omega t plus ym sin of kx plus omega t. This ym is the amplitude of either wave. So we can take ym common, so we get sine of kx minus omega t plus, this ym should not be over here. This has been taken common, so this ym is wrongly written over here. So now we can apply a formula to this sine of kx minus omega t plus sine of kx plus omega t. So ym, as it is common, and we apply the formula of sine of alpha minus beta plus sine of alpha plus beta. So the relation will be 2 sine of alpha plus beta by 2 cos of alpha minus beta by 2. So this gives rise, this omega t is cancelled out, and kx will give you 2kx, so 2 is cancelled with this 2, so this is sine of kx, while this is over here kx and kx are cancelled out, and minus omega t will be minus 2 omega t, 2 cancelled, so this is minus omega t. As cosine is an even function and cos of minus omega t will be cos of omega t. So you get 2ym sine of kx into cos omega t. Look at this equation. We have discussed that a traveling wave should always be represented by a wave function of the form f of x minus vt or kx minus omega t. But here the sine of kx and cos of omega t are in a product form. This is f of the two functions are like f of x and g of t. So this is not a traveling wave, rather we call such a wave as a standing wave. Look at the quantity in the brackets. The absolute value of this quantity gives the amplitude of a standing wave at position x. So if we change x, that will change sine of kx, and ultimately it will change the whole quantity to ym sine of kx. So it means that at different location the amplitude is not the same for a standing wave, while for a traveling wave the amplitude is same for all the points of the stretch string. So remember that the amplitude is determined by the absolute value of 2ym sine of kx for the resultant wave, and this is not the same for all points, that is for all values of x. So from the above equation we see that for all values of x the amplitude is not the same. Those points for which sine of kx is equal to 0 are known as the nodes, and nodes of are those points which have always 0 amplitude. That is, these points will never move, they will always have 0 displacement, their y will be 0. So for such points where sine kx is equal to 0 implies that kx is n pi. When the angle is 0, pi, 2 pi, 3 pi, 4 pi or any integral multiple of pi, you will have its sine to be equal to 0. So this implies this either kx is equal to 0 or pi or 2 pi or any integral multiple of pi. And if we put k is equal to 2 pi by lambda, so we have x is equal to n lambda by 2. So the points, that is the values of x which are equal to n lambda by 2, those points will always represent nodes, means that their displacement for the resultant standing wave will always be 0. So for x is equal to 0 means that at the fixed end of the string there will be a node. N is equal to 1, there is half wavelength beyond x is equal to 0, again you will find a node, and so on. And at these points completely destructive interference occurs always. Now look at the other extreme, where the sign of kx has maximum value. So what can be the maximum value of sin kx? That can be 1, because sin of kx cannot be greater than 1. Maximum value of sin kx be 1. So 2ym sin of kx का जो mod है वो आपको देगा 2ym, that is the displacement of the standing wave will be double as that of the individual wave at the positions where sin of kx is 1, which implies that kx should be equal to pi by 2, 3 pi by 2, 5 pi by 2, or you can easily say that any odd integral multiple of pi by 2. So we can write this as n plus 1 into pi by 2. This is wrong. No, this is not the general situation. Okay, make it 2n plus 1 pi by 2. This will now be an odd number, and for n is equal to 0 you have pi by 2. For n is equal to 1 you have 3 pi by 2. So now the relation is pi. So this will imply that x is equal to n plus 1 over 2 into lambda by 2. What we have done, that k has been replaced by 2 pi by lambda. So in terms of lambda you can have the relation that x is equal to n plus half lambda by 2. So at the position where x is equal to 1 over 4 lambda, you will have a constructive interference. N is equal to 1, so 3 by 4 lambda, again you have a constructive interference. N is equal to 2, so x is equal to 2 plus 1 over 2, 5 by 2 into 1 over 2, 5 by 4 lambda, you again have a constructive interference. So at these points the amplitude will be maximum, that is the amplitude of the standing wave varies with position. Now we come to the reflection at the boundary. So if we have a stretch string that is fixed at one end and the other end is free, so that a source oscillates the other end sending waves through the string, so the waves will be reflected from the fixed end. So that fixed end can be of two types, either a hard point, that is a rigid support, or a loose support. So let us describe these two situations. Over here in this figure we have figure A and B. So let us discuss figure A first. We consider a single pulse along the string. This pulse is sent from the right side and goes to the left towards this fixed end. The end of it, this end of the string is fixed with a wall. So as time passes, this pulse becomes closer and closer to the end, and over here this completely goes to the fixed point. Now what will happen in this situation as this pulse is aroused at this point? This stretch string, as it has a pulse, or we can say crest, so the tension in the string at this point will exert a force on this fixed point, on this fixed end of the string. That is, the string will exert a force equal to the tension in the string on the wall, but this string cannot move the wall up. So what happens? The wall will exert an opposite force of equal magnitude on the string, and that results in a pulse sent back through the string in opposite direction. So we say that here, when it was incident, it was a crest, and when it is reflected, it is a drop. Means that the phase of the wave is shifted by 180 degree. So now this drop will move back through the same string. This is the situation of a single pulse. But if we are sending a wave along the string, so always crest will not arrive at this fixed point, but when the crest arrives, after the crest, a drop will arrive over here, and the situation will become like this, that when crest arrives over here, that is reflected as a drop, and when the drop arrives over here, that will be reflected as a crest, giving rise to a situation like this figure A on the right. That is, when this wave is incident one, y1, and y2 is the reflected wave. So what happens that at this location, this is a snapshot at a particular time, which gives rise to a completely destructive interference. And at this point, there will always be a node at the fixed end. Now, if we consider this end to be a loose one, means the string is connected with a ring, a light ring, and this ring is free to move along a cylinder or a rod without any friction. So when the pulse arrives at this ring like this, it will exert a force on the ring in the upward direction, and the ring is very light, so it is moved up. That is, at this position, the amplitude of the wave has been increased, and the wave is reflected, this pulse, if it is a crest, so it is reflected as a crest at this end, and always we have a node at this point, at this location, that is, the amplitude will be maximum at this loose end, and the wave, the reflected wave, will have the same phase as the incident wave at this point. So when the reflection occurs at the free end, the reflected and incident waves are in phase with each other at that point, giving rise to the constructive interference. Thank you.